Miss Aarti, please stop the video.
Good morning, Lisa. Good morning. Your sound is mute, I think.
Sir, shall I start?
Just a minute, just a minute. Hello, Elisa. Your sound is mute, I think. Hello. Hi, Elisa. Your sound is in mute.
Oh,
Yes,
yes. Now
yes.
maybe it's working. Yeah, yes, okay. It's the first time that I do it with
Yes.
this software, so then I was okay. So that's
Good morning.
good morning. So
Morning.
yes,
So,
and
hmm. So our students are eagerly waiting for your interesting talks, and
yeah, okay.
yes,
So then
especially yes, the students are especially from UG and PG students, and they are in chemistry, pharmaceutical, and biotechnology students. They are very much interested to uh, to your talks. Okay, we are waiting for this. Okay.
okay. So then I hope that that everything will work well. And so then first of all, thank you very much for the invitation. is a nice opportunity, and is also amazing that we can do this with so thousands kilometers apart. And so that's thank technology. Sometimes is good, and and so yes, now I hope that I can do everything correctly. So that's how I can share. Sorry, I have to share my screen. Is maybe this present now? I don't know. Where is the sharing
Just
button?
minute, Elisa, just a little bit introduction, then you can start.
No, okay. So yeah, just no. So then I just make my presentation. Okay, so that's yes. Sorry, oh, what is this? Not now. Okay. No, okay. So no, that should be that one. So did you see my presentation? Do you see it?
Not yet.
Not yet. Okay. So I guess that I have to share my screen. So then but I don't see how. Turn caption, present now, more option, more option. Full screen. No, yeah, but that's me. So where is this? God.
There is one button that is yes, present now. Yes, present now. Then yeah, you can entire
Yeah,
screen. Yeah.
this yellow
Yes.
button.
Hmm. Not yellow button.
Oh God. Sorry, I mean,
There is a
so
video button. Then after,
the yellow button on the top left top is this.
yeah, it is a
Uh,
just middle one, and it is written that present now. Present now. You click. Yeah. Then entire screen.
that's is I hate this such a problem. And so, do you see now the
Hello, ma'am.
presentation?
Ma'am,
Not yet.
ma'am, there's a present now button just in the center of the smiley and the hand. Just look at the bottom of your page.
At the bottom of my page.
Yes, sir. Ma'am, just between the smiley and the hand emoji or the emoticon, whatever it is.
Okay, is my
There's one
okay? Yes.
upward arrow which says present
Present
now.
present now. Okay, yes,
Yes.
that was okay. So that says thank you. And so then I should allow select the window screen. Yes. So then I select and we'll see which the problem
In
is that
entire screen, it will be better. If you share entire,
I
yeah.
okay, I have to see because I don't see the screen. And so, yes, I see, should be this one. Okay, so allow. I think that we are getting there. So now you see most likely my screen, and I can start my presentation. Do you see me now? Do you see the presentation now?
Yes, ma'am, it's
Yes, yes,
visible.
yes, it's visible. Yes.
Yeah, okay. So, and do you see it as a full screen? So, or a double screen? Do you see really only one slides?
No, it
Ma'am,
is
double
a double
screen.
screen. So you
Is a
have to
double
share
screen.
with, yeah, you have to share with your entire screen. Then it will be only single.
Okay. So what I have to do now? So why? So now you see my screen, or so now you see the presentation.
Yes, 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 yes.
Yes,
It is
and so
fine.
now I go to full screen
Mm.
and
Yes.
and you see it.
Okay, okay. This is okay.
So You see, and you see only
It's
one
okay.
slide and not two. So
Yeah,
because I on my screen I see the present slide and also the next one, but you see only one. Is it okay?
Is it okay? Is it okay?
One we see two
Is it
slides,
okay?
but it is okay.
Yeah.
So you see
So
both slides. Okay. Yeah. I don't know how to manage because okay, I just have an option. I just because I have two screen and I think that I just try a very last things and then okay. Now do you
yes,
see
yes,
only
yes.
one
It's
slide?
okay. Yeah, yeah.
Now it's a
Okay.
single
Yes.
screen.
And okay, and you see also the arrow as a cursor
Yes,
that I can point.
yes,
Okay,
yes,
so
yes,
let's go in this way.
yes.
Okay,
Just a
so
minute. Just a minute. Can you
yeah,
start?
Okay, sir. Good afternoon, everyone. I again welcome you all to our web course. Now, I would like to introduce you to our international speaker, Dr. Aliza Bombada, and she will be presenting on the topic Principles of Fluorescence Spectroscopy, Part 1, Steady State. So, Dr. Aliza Bombada is an assistant professor in the Laboratory of Bioimaging and Pathologies at the University of Strasbourg, France. She studied physics at the University of Milan and the University of Florence, Italy. In 2000, she obtained the PhD degree in biophysics for a work carried on at the University of Strasbourg and at the Max Planck Institute for Biophysics in Frankfurt, Germany. Dr. Bombada has received several national and international awards, including a Boehringer Ingelheim Scholarship, a Marie Curie Individual Fellowship from European Commission, and a junior professorship appointment from the German Research Foundation. Dr. Bombada has published more than 30 research articles in international scientific peer-reviewed journals, and she gave more than 20 invited lectures. Her major scientific interests focus on the investigation of the thermodynamics and the kinetics of the interactions of biomolecules, as well as on their conformational dynamics by fluorescence spectroscopy and other biophysical techniques. Therefore, I would like to request ma'am to kindly deliver her talk.
okay. Thank you very much for the kind introduction. And so then let's start to talk about fluorescence spectroscopy. Okay, so yes, yes, okay. So first of all, I just cite the literature that I was used for preparing this talk. And of course, the two major books on fluorescence spectroscopy, which is the Principle of Fluorescence Spectroscopy of Lacowitz. We call it the Bible of fluorescence spectroscopy, and the molecular fluorescence of Bernard Valeur, which is also a very interesting book. Then I would like also to give some credit because to compose this lecture, I was getting inspired by lecture and the seminar of other great scientists, then very famous also in fluorescence spectroscopy, actually, like Professor Jameson of our university, Professor Wolf from the University of Prague, Professor Mély of University of Strasbourg, and also Dr. Julia Karpenko from the University of Strasbourg. Okay, so let's go. What is, so let's say, emission of light. That's what we'll actually be interested on. And emission of light, we can say luminescence, and we can define luminescence. And luminescence is the excess of light emitted above thermal radiation. So is light. So is emission of energy, and is light and not heat. Okay, the emission follows after the molecule has receded for some time in the excited state. So then we need to excite our molecule or atom also. And then the atom, the molecule will release the energy, and part of it will be light. Okay, so according to the excitation mechanism, we can define several types of luminescence. And so I start from the bottom. So then, for example, if we have a chemical reaction that is providing energy, so it's an exothermal reaction, so then we excite through it and we will get chemiluminescence. If we use heat, we can have thermoluminescence, we can use an electric current to provide energy, and electroluminescence. But what we will be interested in this course is the photoluminescence. And actually, I see that there is maybe a little bit of problem. It's not ion of light, but is excitation of light. So is excited through excitation. So absorption actually of light is the mechanism with which the molecule will be excited, and so then we will get photoluminescence. And photoluminescence is divided in fluorescence and phosphorescence, which actually both actually we are interested in, but mainly is fluorescence our topic. Okay, so what is fluorescence? But fluorescence then is the light emitted by an atom of a molecule after a finite duration, which will be then defined as a fluorescence lifetime, subsequent to the absorption of electromagnetic energy. And so how to separate between fluorescence and phosphorescence? So the emitted light arises from transition of the excited spaces from an excited electronic level to a lower electronic level. So when this is happen without change in electronic spin, then we have fluorescence. And that's what we will see when we will focus on the Jablonski diagram. That's typically happen between the first singlet excited level, S1, and the ground electronic level, S0. In contrast, when the initial and the final state have different spin, so from a triplet to a singlet state, then we have phosphorescence. Okay, so for getting into more physical and chemical definition and phenomena, so some story, because it's actually quite interesting. I found it also myself to see how this, because that's fluorescence is known actually quite some time. So this is a piece, some of linium nephriticum wood into water in an alkaline solution, and is illuminated with a UV lamp, and we have this bluish color. So sorry, I cannot go further. What happens here? Okay. So I don't know what happens. Yes, now it's going on again. Okay, so and then so we are in quite late, so in 1577. It was a Spanish Monardes, a Spanish physician that actually observed this bluish opalescence color in water infusion from this wood. Then afterwards, another scientist. So now we get more and more closest years. So actually, I think that there is a problem. So it's not 1916, but it's 1615. So okay, because that would have been quite a good step. But okay, so so that's was identified actually this wood, and then more recently the molecule really was isolated. Okay, so then let's go on with the history. So Robert Boyle, which is famous in thermodynamics, report investigation of this system. And actually what is discovered that addition of acid abolish the color, and the addition of alkali brought it back. So practically the first pH indicator was observed some centuries ago. So then let's go on. So that's Herschel was a German scientist that it observed the fluorescence from quinine sulfate, which is a molecule that we will talk again about it because it's a fluorescence standard. Now we use it as a fluorescence standard. And then we arrive to George Stokes, who created the term fluorescence. And actually, he's also made another observation. It observed that using a prism to obtain ultraviolet region of the solar spectrum, so then below the 40 nanometer, to illuminate a quinine sulfate solution. So he observed that the emission could be observed through a stained glass filter above 400 nanometer, which was blocking the excitation light. So this observation is quite fundamental because that proclaims that fluorescence is of longer wavelength than the excited light, and led practically to the principle that nowadays is called Stokes shift, and we will see it also in more in detail later. Okay, I may let appear everything because there are some problem of order. So then let's go on. So in 1871, so there was fluorescein, which is one of the most famous fluorescence probe, very fluorescence actually, was discovered and synthesized actually. And then Mayer was the first that used the term fluorophore to describe a group which is associated with fluorescence. And so fluorophore, so it's a word that comes from Greek. In ancient Greek, phore means bring. And so then, yeah, this molecule, a fluorophore, brings fluorescence. Closer to us, so we have Gregorian Weber, which was then synthesized Ansil, a very also famous probe, and actually initiated the field of quantitative biological fluorescence, which is basically the father of our discipline. We all are biophysicists, and we use fluorescence to investigate biomolecular systems. And so then we arrived to Shimomura, who was the one that discovered the green fluorescence protein. And he was also awarded of the Nobel Prize in 2008, together with Chalfie and Tsien, for exactly this discovery. And so then I stop here because there are, yeah, of course, then afterwards, yeah, it's our work that is involved. That's where the milestone actually of fluorescence spectroscopy. Okay, so then let's go to the, so let's stay also a little bit in the history, but just to see what are the major concepts in fluorescence spectroscopy that we will also analyze one by one. And they were actually, this concept were clarified, were coded in the last century, like the excited lifetime, the quantum yield, the polarization of fluorescence, and the Jablonski diagram. And also the fluorescence, actually resonance energy transfer. We will see why fluorescence should not be used in this term, Kasha rules, and so on. So, okay, so exactly because of this concept that I just listed, that's are the important characteristic. So all fluorescence data that we acquire when we study when we study a system with fluorescence spectroscopy are practically the ones that are listed here. So the fluorescence emissions spectrum, or the excitation spectrum, also the quantum yield, the polarization, the fluorescence lifetime. These are the parameters that we will use to study our system. And we will go through them step by step. And of course, also we will talk about quenching by external quencher and the resonance energy transfer, which are also based on the parameter that we have listed just here. Okay, time by time is stopping. Okay, why? What is this? I have the feeling that it's when I move. Okay, what is not possible? Oh. Oh, is blocked, and I don't know why. Okay, now it's they are away. Okay, then just shortly, why we use fluorescence? Because fluorescence actually provide a lot of information. Here, just very schematically, few of them. So then you see it. So let's say that that is our, let's say, molecule, or it can be a protein or whatever other, or a nucleic acid. And this is the fluorophore. This pin is the fluorophore. And so, because the fact that this there and this provide us a signal, we can get a lot of information, which are mainly structural and quantitative, of course, also, because the fluorophore inform about the environment around itself. If we use it, we can measure the accessibility of it. And so then we can also have information, confirmation information. We can measure distance, and that will be with Fred. With anisotropy, where we are practically analyzing the rotational mobility of the fluorophore, we can get additional information about the dimension and the conformation. We can have information on excited state reaction. And molecular environment, dynamic process on the nanosecond time scale, which is the 9th time scale of fluorescence, is very selective and is also very sensitive. And then, based on this, actually, fluorescence probe has been developed to inform about particular physical chemical properties, like viscosity, temperature, pH, polarity, the presence of ions. And about sensitivity, we can work with the subnanomolar concentration, and femtomolar and even single molecule with some effort can be reached. Okay, so that's are just the wavelength scale. Sorry. And what we are interested in when we are using in when we work with fluorescence spectroscopy is visible light, of course, UV in many respects, and also the infrared. So let's say near UV and the near infrared. That is our scale of wavelength. And so, yes, that's how it is. And that is important because actually these wavelengths are much lower in than the dimension of optical elements, which is not the case of microwave and radio frequency technique, for example. And so that's and space, and moreover, is instead this wavelength is larger than the dimension of the molecule that we are studying. And that means that the whole molecule sends the same phase of light, in contrast to X-ray diffraction. Of course, that's with this, I don't want to say that fluorescence is better than X-ray, for example. Simply, we get different information from out of it. And of course, for a comprehensive understanding of a system, there are several techniques that need to be used. But let's be happy about fluorescence now. Okay, finally, let's go to the mechanism of fluorescence. And here I draw a schematic, so Jablonski diagram, which is actually the basis, the backbone with which we are understanding the phenomenon of fluorescence. So here what I draw is the ground state is S0, and the two excited state, singlet excited state. So the first things that we are doing, as we were saying, so we need to send the molecule to the excited state. So, and we do it through light. So then light will be absorbed, and the molecule, according to the energy and therefore the wavelength, is promoted to excited state. If the energy is high enough, it can go to even the second excited, the singlet excited state. But normally with internal conversion, since there is even an overlap between these two states, it's go immediately to the S1. And from there, there will be a rapid vibrational relaxation, which makes that independently of which vibrational state was heated, all the molecule we will find at the very first of the vibrational state of the first excited state. And from there, it will go back to the ground state, because it's a metastable state. So then it's not happy to stay there after a certain time, of course. And this excitation, so from the M star, so the excited molecule, to the M, the ground state molecule, can be obtained by emission of a photon, as I was indicated here. Kf is the radiative ray constant, and this is exactly fluorescence. And that is what we actually, so from the in black is the absorbance spectrum, and in orange is the spectrum of fluorescence, that is the profile of this emission. And so here we immediately see the stock shift aspect. So as you see, due to this vibrational relaxation, the energy emitted is less than the energy that was used for exciting the molecule. So since this is the energy is as a proportionality, inverse proportionality to the wavelength, so less energy means larger wavelength, and that means that the emission spectra is shifted to larger wavelength with respect to the absorption of excitation spectra. And so that is the Stokes shift as Stokes was observing. So, okay, but not all, that there is not only this mechanism of this excitation. There are also many others mechanisms. And for example, internal conversion. And okay, so let's say all these other mechanisms that now I will cite are not associated with the emission of a photon. So that means that there will be a part of the energy that is emitted on the form of light and a part not. So this explains that the quantum yield, so that the yield of our fluorophore, it's not 100% because part of the energy is not seen as a photon of light. Okay, so then just I list, so now there is the internal conversion, as I said, then there is the intersystem crossing, which is actually a transition from the singlet to the first triplet state. And that is not allowed transition, so that's probability is very low, but it happens, and is not allowed because it's required also a change of spin, but it happens. So then and actually when the molecule is on the triplet state, will happen that a similar phenomenon. Okay, so sorry, that will be after. So then you see a part of the energy goes in another state. Then we can have also some collisional quenching. So this is a molecule, so collision with other molecule, and so that's quenching, and is also associated to it and so that's what I want to say. So that is we have the rate constant of fluorescence, which is the radiative one, and we have plenty of non-radiative rate constant according to the system, which are not associated to the emission of a photon. And so when the molecule, just for completing the process, when the molecule is on the triplet state, will get the same phenomenon, go through the same phenomena, vibrational relaxation, and then emission. That can be an internal conversion, and also emission of a photon can go down from the triplet to this S0 with emission of photon, and this will be phosphorescence. So now we have seen fluorescence here and phosphorescence is here, which of course occurs at a even farther wavelength, because the energy is even less. But we are not interested to this type of signal here, and so let's go on with fluorescence. Okay, so this is just a sort of another way of representing the same things that I was seeing, and then here exactly you have, according to the energy associated, the spectra associated to the different transitions, so S0, S2, for example, S0, S1. And now here we have emission, that is fluorescence, S1 to S0, and phosphorescence, T1 to S0. And we have also the time scale of the phenomenon. And so according to what I was saying, so vibrational relaxation is very fast. So where is it? Yes, here is a picosecond scale. So and instead the fluorescence spectroscopy, fluorescence lifetime here, as you see, is in the nanosecond time scale and even hundreds nanosecond scales. Okay, so then practically vibrational relaxation is something that can be considered immediate. So that's why we don't observe it. We observe immediately the fluorescence spectroscopy. Okay, so before speaking really about fluorescence, we have to speak about absorption, because there is no fluorescence without absorption. And that's also is a part of the quantitative analysis that we have to do. So absorption is of electromagnetic wave, consists in the process by which the energy of a photon is taken up by matter, typically the electrons of an atom and or a molecule, and of course it absorbs if the energy of the photon match the energy of the electronic transition. And so okay, we can define this the oscillator strength, which is actually is the molecule has to be seen as an oscillating dipole. So then that is and at least in this model is seen like this, and the oscillator strength is a dimensional quantity expressing the strength of the transition. So that's a bit very theoretical, but we can just see in this parameter that it's the oscillation strength that tells us the strength of the transition is related to the absorption spectra, or better, the absorption spectra, which is actually this part here, is related to the oscillator strength, so to the ability of the molecule to absorb light. Okay, so then now let's see how we can go to a practical use of absorption. And so here I was making just a model, so just to say what happens in your sample when you illuminate it with light. So in gray is the cross section of the incident beam. So then is the beam of light with which you illuminate the sample. And in rosa, you have the molecule. So they are illuminated, and of course, the number of this molecule depends on the concentration. And of course, let's say it's a molar concentration in each mole. You have a number of Avogadro of molecules, so that is the number of the molecule in a volume. In a certain in the volume that is represented here. So S is the section, and the L is just the height of this element of volume. But what we are interested on actually is the ability of a molecule to absorb the light. So we define the molar absorption cross section, which is the brown circle, which is actually a geometrical parameter which is proportionally to the ability of the molecule to absorb light. So that's what cross section in physics means. And of course, the cross section is not as large as the molecule, because the molecule has a certain probability of absorbed light. So, but that is what we are interested in. And so, if we want to calculate the fraction of light that is absorbed, we have to make this calculation. So then we have to multiply the cross section by the number of molecules that we have in this little volume. So then we have really the fraction if E is the initial light, so which correspond to the section of the beam. That is like the whole light that I was sending, the whole photon. So dE is just the fraction that is absorbed. Okay, so then mathematically you can follow. And the fraction of light absorbed, probability of photon capture. That is, we can say it like this. So we go through some mathematical, so we just integrate to have so that is just an infinitesimal volume to have it in all the sample. And we integrated that, so then we have a logarithm, and then we pass through a decimal logarithm, and and we call of this, so that is the mathematical result, and we will collect, we join some of these parameter in this parameter epsilon, which is actually what we call the extinction coefficient, which we really practically use every day in the lab. And so the ratio, so if, and this actually, this how to say, this ratio, so E is the light that goes through, and D0 is the light that was sent to our sample. So this is the transmittance. Of course, that's we are not interested about transmittance, even if transmittance is what is measured. And we define absorbance as the minus logarithm of T. And that is, so then is this quantity here. So then it's just, that is minus logarithm of T, inverting the argument, the E and E with zero. And so that is actually an extremely important law that we have now built up really quantitatively. And that is the Beer-Lambert law. That is extremely important because it tells us how we can determine concentration of our sample by measuring the absorbance if we know the extinction coefficient, which is in most of the cases is known. Okay, so yeah, just some yeah, that's maybe, I see that actually the time is quite far. We lost some time in the beginning, actually. I'm very sorry, but we will catch up. So just here some, if there are some physicists among you, so then maybe it will be also interesting to see how we can go from the photophysical phenomenon to the spectrum that we are actually measure. So this, you see, that's are the two electronic state. And the line, the gray line, are the vibrational energy state, and that's is and the little mountains, let's say, are the probability of finding a molecule in this with this energy. And so then you see, let's say that I provide an energy that it allowed to go from this level here to that one. So it's the black arrow. And so yes, it will be absorbed because is a transition between two existing levels. It will not be absorbed if it will follow in between, let's say, but it is absorbed because the level exists. But as you see, okay, here the molecule is very much present, but it arrives where at the point where the molecule is not very much, the probability of finding a molecule is very low, which this will be reflected in a very lower level lower probability of this transition, and which is instead larger with the red arrows that arrive here, even larger with the green arrows. And so this is reflected in the intensity of the spectra. So the height of the spectra, it tells us the probability that this transition is occurring. And so we can build up the spectra in that way. So, okay. Just to see how they looks like, but we will talk more when we will talk about the probe, or or maybe here, as I said, I go a little bit quickly, because we will talk again when we talk about the probe. So let's say that the molecule that absorb well in our spectra of wavelength, that, so as we said, UV and visible, so are molecule that present some degree of conjugation of p bonds, and so also ring. But as I said, we will talk again about this. Okay, so then, as I said, we build now our emission spectra. We were talking about absorption, but actually for emission is just the other way around, but the principle are the same. So then we have to we have to follow this transition, this yellow line, and so then we have different probabilities. So the thickness of the error that is here is the probability that this transition is occurring according to occupation of the state, and this probability is reflected in the emission spectrum. The same story as we were seeing with absorption or excitation, and we have our spectrum. Okay, so actually, as you see, I was using absorption and excitation somehow in the same circumstance. And in fact, in principle, one is expected that the excitation spectra matches the absorption spectrum. But this is often, it happens, let's say it happens, but not always. And that is actually so I insist a little bit about this, about what excitation spectra are. So maybe I go back to my slides before. So excitation spectra, as I was drawing here, is not absorption. So properly said, is excitation, is fluorescence. Sorry, we measure fluorescence. So that is fluorescence. And so actually it's true that we measure this transition, but actually the question is another one. You don't want to see the probability of absorption, but the question when we measure an excitation spectra is, so I fix the emission at one wavelength. So then I fix the emission at one wavelength, and I ask to my fluorimeter, let's say, because what are the different wavelength of excitation that or let's say like this, where I have to excite my fluorophore in order to have higher probability of seeing the fluorescence at this wavelength. So this is practically the probability of the of excitation in order to observe the fluorescence at a very specific wavelength. So yes, of course, it's similar to absorptions, but as we said, not always. And we see when that's not happen. The match occurs only when there is a single species in the ground state and no reaction occur at the excited space. So then we have quite a match, like is represented here among the point and the line. So fully matches between excitation and absorption. So let's see the example where it doesn't happen. So that is for example when we have an excited state proton dissociation. So so here we have let's say sorry, I was also missing another point that say that normally, as we were showing in the slides before, there is a mirror rule, a mirror effect between the emission and the association and the spectrum. And so we'll see when that doesn't happen. So here we have an example of a molecule, this one, that's deprotonate, and that is the ground state, and that's but it deprotonate also at the excited state. So that means that I can excite my molecule, and then while she is it is at the excited state, it deprotonates, and then fluorescence with the mid. And the pK in the excited state is lower than the pK in the ground state. So let's say if this is 7, or it will be, or yeah, that will be, or 4 or something like this. Okay, so then this is what happens. So if we are at acidic, so then pH 1, for example. So another point, fluorescence is occurring from the deprotonated molecule. So that is the fluorescence part. So and so that is the spectrum that we have in green. And so at pH 1, how to say, we are here. This deprotonation doesn't occur because the pK is much higher. And so then is the molecule, the protonated molecule, that get excited, and then this occurs because it's and we can see then fluorescence. So instead at high pH, basic pH, like for example here 13. This deprotonation occurs already, so it's already there in solution before that I excite. So practically, it's like it's this species that I excite already, the fluorescence one. And so you see that will be the spectrum of excitation that is symmetrical to the fluorescence, because now it comes from the same species. It's like in the solution there is only one species. Instead, before at acidic pH, I was excited a different species. So the fluorescence comes from a different species. It comes from the deprotonated one. Instead, I excite the protonated one. So that is an example. And then the can be excimer formation and the excited state, and exciples, which is actually a similar story. So excimer is just forming a dimer on the excited state. So again, something that happens in the excited state, and so then I will get the fluorescence from a different molecule than the one that I was exciting. And exciples is forming a complex, in this case with different molecules, that can happen in the excited state. Is favored in the excited state. And also there is also an example in which fluorescence I get it from a different species instead than the one that I was exciting. And so, as you see, there is no symmetric rules. Okay. Fluorescence is very sensitive to the environment, and so notably to polarity. And so let's see why. And so then we can call what solvent relaxation is. So that is so then, as you see, molecule, as we were seeing, they are represented as oscillating dipoles. Then is our red is our molecule that I excite, and in blue is the solvent. So in this case, the dipole in the emission in the excited state is different from the ground state, because there is an emission dipole and the absorption dipole. We will see this when we will talk about polarization. Good. Since the excitation is very fast, here we are in the 10 power minus 15, so it's really extremely fast. So the solvent doesn't succeed. There's not enough time to rearrange around this new dipole, and it takes a bit longer time, and this, while it's doing this, is so this is the relaxation, because that is a higher energy, because it doesn't want to be there, so it's yes, to be relaxed, and by doing this, from where actually then fluorescence occur, so of course is relaxing, is the energy is decreasing, and so fluorescence is occurring at a lower energy. Voila, that is the solvent relaxed, and means higher wavelength. So this is an important parameter which will be used in how to say, in to study the environment of the fluorophore, so the wavelength and so on. So now I'm asking yourself, as I was no, actually no, I was thinking that I am already late, but actually I have 1.5 hours. That's it. So then I can go on. So then okay, that's good. That's fits. Okay, so yes, so that is the phenomenon of solvent relaxation, and so we see how the wavelength in which we observe an emission spectra can inform us about the polarity of the solvent. Okay, so now let's start with another important argument, which is polarization, and which will bring us to define fluorescence anisotrope. Okay, light is an electromagnetic wave. So as is represented here, so you have an oscillating electric and also magnetic dipole perpendicular to each other. Okay, we interested to the electric dipole in this phenomenon, and so yes, that is what happens when so the normal light. So if a light, so let's see how a polarizer works. So the light source, when it's unpolarized, which is the case of the natural light, for example, and is passing through a polarizer, which is a device that can isolate one direction of the electronic vector, because, for example, it absorbs effectively one plane of polarization, and or let's say it absorbs actually it transmit effectively. So that's here I have to correct. So that means that it absorbs all the others, and it let pass only one plane of polarization. So then we select practically only one plane of polarization. So just I note that I have to correct, transmit. Yeah. So, and then we can use another polarizer, and that is called normally analyzer. And if is oriented differently, so then it will not let pass the same direction of polarization, and so practically afterwards is black, you don't have anything else. The light is not passing through. So that's somehow is the principle of the sunglasses also, that used to protect from the UV light. Okay, so that's as much polarization. So let's go to molecular system. So yes, we have to define the transition dipole, and so because that's what we are working on. So dipole, that's a direction of polarization. A dipole as a direction, and so yes, that's just a little bit of quantum physics, just very, very light. And so here we have a transition practically between these two molecules, and the transition moment, will be the transition moment, is represented the transition dipole resulting from the displacement of charges during the transition. So when we provide energy to a molecule, something happens in the molecule, so the charge distribution will change and so on, and we can define this dipole transition. So which is not really a dipole as we consider it is in our when we say, for example, the dipole of a water molecule, and so then it's just some you have a positive and a negative charge linked by a vector. yeah, it's not exactly this, but it's look like. So then it's because it's related to different charge distribution from the two sides, let's say, of the dipole. Both absorption and emission implies electronic transition, and there is in fact an absorption transition moment and an emission transition moment. Okay, so let's see what happens when light interacts with the material. So what I represented here, I represent in gray is, let's say, we assume to have a polarized light. That is the direction of the polarization of our light. And then in the blue and orange are, let's say, are our molecules, so it's the material. And so if we look at the very first system, which is, so we see that, let's start with blue. So that's what we have represented here are the absorption transition moment of each molecule. And in average, of course, the average of the solution, that is the transition moment is this dark blue line. Of course, they are all parallel, and it's a very rigid system, a very ordered and rigid system. And it's so rigid that during the lifetime, it doesn't move. So that means that nothing happened more, and the emission dipole in this case is also oriented as the absorption dipole. So, but let's stop to the absorption before going on. So this is the way in which our light, our dipole, interact with our excitation light. So the dipole of the excitation light interact with our system. So that is a scalar product. And that is practically that we call it photoselection, because that gives us the probability of exciting the molecule. So it depends of the orientation between the excitation dipole and the absorption transition moment of our molecule. If they are parallel, it's great. So then the cosinus is 1 because the angle is 0. And so then we have all the molecule will be excited in the same way. If we are if the molecule are oriented differently, so it's less ordered the system, so they will not be or excited in the same way. So in average, that will be, let's say, the transition moment, and there is a sort of angle between it, and so then it will be less. It will be less. So will be the photoselection. And so on. Okay, so that is concerning absorption. We see also that we can have rigid media, so where we can define rigid media where the system is not changed during the excited state, and liquid media, where instead the molecule reorient, and so of course then also their transition dipole also reorient differently. So then there will also be an angle between the transition moment of absorption and of emission. And is taking care about all this reorientation, and so that we will measure then the fluorescence depolarization, because practically, so in this case, you see, we we don't lose the polarization, so then it's remain, so that everything remain oriented in the same way. Here already we depolarize the excitation light, because it's the photo selection is already one first step of depolarization. And then if in addition also we add some rotational diffusion of the molecule, then we depolarize even more at the emission. And fluorescence anisotropy will help us to quantify this phenomenon. Okay, so let's build up the parameter that we measured when we measure fluorescence anisotropy. So we said that the first step is the photo selection. So as we have just seen before, the probability of transition of a molecule between the two energetic levels, here S0, S1, so let's make the most common way, the most common, what happens most commonly, is proportionally to the cosinus square of theta, which is the angle between the dipole transition and the direction of polarization of the excitation light. We had just seen it before. So, yeah, so what is represented here practically? So in black, you have all the molecules oriented practically with their dipole that is oriented in a different way. This is the polarization of the excitation light. And what is the red bar is practically the probability of excitation. As you see, when the molecule when you see the red bar, when you see only the red bar, that means that there is the dipole of the molecule is oriented also vertically. So that is the highest, the longest red bar is the highest probability, because the molecules are oriented parallelly to the excitation wave, the polarization. And instead, for example, this molecule here, which is the transition moment is perpendicular to the direction of excitation, is practically not excited. Okay, so the phenomenon, the photoselection is the phenomenon of anisotropic distribution of orientation of molecules in the excited states in this sample, which is caused by the polarization of excitation light. Yes, so that means, so since the probability of exciting this molecule is much higher than exciting that one, and actually this one is even 0. So then in the excited state, we have this molecule, but not that one. So in this case is the anisotropic distribution of in the excited state is caused by photoselection. So these are the practical parameters that are used to measure the anisotropy. And so historically, we started with the fluorescence polarization, which is sometimes used, but very rarely. It's what is used, especially in biophysics, is the fluorescence anisotropy, which has actually quite an advantage, because in the denominator, you have the total intensity. And now we see why. So that is so if we excite, for example, with the direction in the zeta axis, so then we have the light, of course, as 3 components, x, y, and z. So then in principle, it's considered and we detect in the y-axis. Later we will explain also why is the geometry for detecting fluorescence is that one. Yes, we cannot say everything at the same time. And so then, of course, what we detect the component, the zeta component, which will be parallel to the excitation, and the X component that is perpendicular to the excitation. But there will be also the Y component. So practically in the total intensity, we have the component that is parallel, the zeta component in this case, and the X and the Y component, which are the same because they are both perpendicular to the excitation. Okay, so the fact that fluorescence anisotropy is defined in that way simplify largely the equation in which is used. Just an example. So this is the anisotropy of a mixture of fluorophore, and Fe is the fraction of such fluorophore. So then you see it's a little bit not very intuitive. Look how it looks simple when we use the fluorescence anisotropy. So practically we have the anisotropy of the mixture, which is just the weighted sum of the anisotropy of each fluorophore according to the fraction of existence, let's say. So that's why we like this parameter more than the other. And okay, so this is just a curiosity, because maybe some of you was already hearing this definition, the magic angle. And what is the magic angle is so practically is an angle where we can collect the emission light, so with the polarizer, so the orientation of the polarizer in the emission beam that allowed to detect a parameter which is proportionally to the total intensity. Not only, so let's say that if we don't place any analyzer, as we were seeing just before, like here we didn't put any analyzer, so there is no polarizer. So we detect the light, and we detect the two components actually. The other one we don't see. The Y component is not seen. It exists, but is not seen in this kind of detection. And how to get this the total intensity, which is done like is composed like this with the two perpendicular component. So we can measure separately the parallel and the perpendicular, and then calculate the total intensity, or we can measure the emission with an analyzer which is oriented under an angle xi, for which E perpendicular would contribute to the passing light with a double weight compared to the E parallel. So practically, that is the equation. So we are looking for we are looking for this angle, because that is the intensity that we will detect. We are looking for this angle for which the sinus is 2. So the sinus squared is 2 times the cosinus square. So we are solving this trigonometric equation, and we will get 54.74, which is the magic angle. So that means that when we put the magic angle, when we see is the magic angle, so the intensity detected through a polarizer oriented with such angle will be like this. Just we calculate the cosinus square of this angle, and you see, so we have the E perpendicular weight twice in comparison to the E parallel. So we don't measure the total intensity, but we measure 1/3 of the total intensity, but we know that is 1/3, so to get the total intensity is easy. So that's is a way, and we will see when we will make a time resolved fluorescence, that is actually the polarizers that is put in the emission beam, to be sure that we get the full light, not distorted due to anisotropy decay. Okay, so yes, now let's see the different phenomena. That's there are. I think that yes, maybe I will be a few minutes late as we were starting late, but I think that I succeed to get through everything. So is okay?
Yes.
I
Yeah, it's okay.
okay, and so okay, let's see what happens in this in the molecule. So now they build up step by step all what happens. So then, yeah, that's our transition moment of the molecule. So then here we are in the case in which we consider that absorption and emission now are parallel, and dipole moment. And so then we want to see the effect of practically photo selection. Randomly oriented the fluorophore without rotational diffusion, excited with Z polarized light. So there is a symmetry around the phi angle. So that's in the cone. So everything's in the cone. So we can integrate and around the phi angle. So these are trigonometrically the intensity of the parallel. So that means Z component and the X component. So that's about what we are detecting. So that is the intensity that we are detecting. And so all the molecule with the same theta, so that's induce the same depolarization. So then if we see the anisotropy of all these molecules, that is just, I just substitute and I get this value. So that is the depolarization depending, of course, on this theta angle. Okay, so, but for seeing the anisotropy, the molecule need to emit. But for emitting, the molecule need to be excited. So it is important also to take care the probability to find an excited molecule with a dipole under the angle theta, which is that one. So that is the photo selection that we have already seen just in the beginning, and this cosine squared, and that is just the size of the cone. So practice, that is just what is, because they have all the same probability, the molecule, because they are all oriented with an angle theta with respect to the polarization of the excited molecule. Okay. So if we put everything together, so this was the anisotropy expected from a molecule oriented with an angle theta. That is the probability of getting the molecule oriented with an angle theta. So we just average to have the average value that we will observe, and of course is weighted through the probability of getting the molecule with this angle. And so we integrate between 0 and p square, p divided by 2, so p and a half, let's say, that is the angle. So theta is moving with this triangle, and we get 3.5. So if we substitute to this 3.5, 3 divided by 5, 3/5, we get 0.4. So that is what is called the fundamental anisotropy. And well, the experimental value is always slightly lower, because there are other of course, it's not completely every ideal solution rigid and everything doesn't move and so on. So in reality, there are other aspects that play a role, but that is the fundamental anisotropy in such case, very particular, that we have described, and is also but we'll see. So, but that is a particular case, as you see, where there is this parallel. Let's see a more general case. If absorption and emission, so I try to respect the color code, are not collinear, which is a more general situation. So there is an angle alpha between the absorption dipole and the emission dipole. So that means that since now we have seen that angle are associated to such factor, so practically we have to add to the 2 divided by 5 that we have calculated before for the more extreme case, also the contribution of this additional depolarization. And so that means that the anisotropy, that is in general, since there is this angle alpha in most of the fluorophore, is not 0.4. And actually these are some value, also some particular value that can be calculated according to the angle alpha. So as you see, for the magic angle, the anisotropy, a fundamental anisotropy will be 0. So the intensity will not be affected by the presence of the anisotropic distribution. For 90, which is the other extreme case between minus 0.2, just we have to make the calculation. So in general, it will be the value of anisotropy, and that's why in the graph we'll see the anisotropy plotted only between minus 0.2 and 0.4, because these are the two limiting cases on the that we can obtain. Okay, so yes, just a very last slide for this section. I just show you a very easy, so a schematic way of using for what anisotropy is used for, what we can do with anisotropy. So let's imagine a binding. We want to determine the binding affinity. So that will be let's say the receptor is fluorescence, so I excite it and it emits, okay? And it rotates with a certain speed. So then it will be associated to a certain anisotropy, because the dipole are changing orientation and so on, as we just have seen before. And then we put it, it binds a ligand, and I measure the rotation. It will be slower because the dimension of the molecule and so on. So the anisotropy will be also different for the complex. And I can monitor the anisotropy in function of the concentration of ligand that I put. So I can practically follow the saturation of my receptor using anisotropy. And then I can also, so let's say it's a simple binding reaction. I can extract also the equilibrium constant, determining the parameter, because I mean, on one side, so to the fluorescence signal that I measure, so phi r, we didn't define yet the quantum yield, but we will see just this later. So that is practically the emitting property, the yield of the emission for the receptor, that is for the complex, and of course the signal is depending of how much receptor I have, how much complex I have. So that is how is composed the fluorescence signal, and that is how it's composed the anisotropy. So that is the anisotropy value of the receptor alone and of the complex, weighted by the fraction of presence of the two spaces, and the fraction of species is of course is represented like this, and is represented as you see, is not only a fraction in concentration, but is a fraction taking in account also with which weight they contribute to the signal. So that is important. So it's practically the probability, that is more than a fraction of presence, that is the probability of seeing the receptor, and that is represented like this, which of course, yes, in this case, which of course is also, it depends of this concentration, but also of his signal. Say the signal is higher, I have a higher probability of seeing, and so of seeing it. Okay, and so then I can, oops, sorry, yes, I can exploit this signal, and I get information on the equilibrium rate constant. Okay, so that will be that is actually an overview of some fluorescence in the steady state. And then afterwards, what we will do is some to consider some practical aspect. Actually, that was more theoretical. So, but then actually practically, what we will do when we do a fluorescence measurement. So now I ask
Yes.
you. So what is the point? A break or I?
Yes, yes.
Let me know.
A few minutes break. Yeah, then we can start the tutorials for this. Yes.
Okay. So and the break will be how long? Is
So up to you. You can take 10 minutes or 10 minutes.
so yeah, I think 10 minutes is enough. Is enough. So just I drink something
15
and
minutes.
I
Yeah.
no 10 minutes for me is also is enough. If it's fine for the audience also, because there are a lot of concepts. Is
Yeah.
I is okay.
So
So let's say that.
audience will. Yeah. So audience will, if you have any questions, also you can ask in the tutorials, okay? And Alicia will explain in the during the tutorials if you have any queries, okay?
Yes. Okay.
Okay.
So
So we'll take.
that means
Hmm.
we will meet at again to so let me see 12. So yeah, for me is 12 12 I don't know what's for 20. So let's no now it's 12 10 or 9 or something like this at 20 or so tell me what is the
Yes. Yes.
it's
So
okay.
we'll take 10 minutes breaks. Yes.
Yes, exactly.
Okay.
Okay.
Perfect. Perfect. Thank you.
So yeah, thank you. Bye.
Thank you.
Yeah. Okay, so
So are you in office or
yeah,
from your home?
um, so
Yeah.
oh sorry, I okay. So then I see you almost all back.
Yeah.
Yeah, okay. And so yes, so then so in this tutorial I will, as I said, I will provide some uh, practical aspect of when fluorescence measurement has to be taken, and so also some troubleshooting. That means that yes, okay, we measure a spectra, but we'll see what is the signal and how to correct it also according to the different situation. So I will just try to. I don't know about the question. If there are questions, of course, on one side you can interrupt. In principle, you can interrupt me at any time, but so up to you. So or at the end. Just
Yes.
I will.
So if you have any questions regarding this lecture, also you can ask. Yeah. And
Yeah,
Alicia will start also the tutorials. So you can both any questions you can ask, and you can interact with Alicia.
yeah.
Okay.
Okay, so then yeah, and now I hope that I will find my. So that was, yes, that will be. Now I guess that we are. Do you see the lecture or not? Do you see the screen? The screen?
Not yet.
Not yet. Okay.
No.
Yes. In fact, I was. Ah, la 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 la. Okay. Where is so entire screen? Wait a minute. Because this. Allow. Yeah, but now you see, and we'll see. Ah, okay. You are presenting. That is okay. And so, and now, do you see it? Do you see
Screen is
the
seeing.
slide?
No
So
slides,
you
but
see
screen is visible.
not the slide. Yeah,
Screen, yeah, screen is visible.
yeah. And so also now you don't see my presentation. No. So
No presentation.
because I don't see the same things. I stop presenting, so I make stop presenting, and what why so I was clicking and presenting. Now I have to select my screen, and why I don't see the presentation screen? I enter meet entire screen. Let's try with this. Let's try with this entire screen. And now?
Yes, perfect.
Now it's okay. Okay.
Yes, perfect.
So,
Yeah, it's visible.
okay. Oh,
Yeah,
that's fine.
perfect.
Yes. Good. So, yes, fluorescence practical aspect. Let's see. We see. But of course, we have to start with absorption because, as we know, there is no fluorescence without absorption. And absorption has also some value itself. So there are many experiments that can be done by exploiting absorption signal. So we have seen the Lambert-Beer law practical, or let's say this is the relationship when we were discussing about the Lambert-Beer law. We were seeing also the relationship between the absorption and the transmitter, or let's say absorbance, more correctly, absorbance and transmittance. And actually, what is measured in a spectrophotometer is the transmittance, because we illuminate the sample with a known intensity, and then we measure what is goes through. We cannot do anything else. We measure, so there is a detector, and we detect the light that goes through. The instrument, of course, is made that it's calculate for us the absorbance. So then the signal that will be given is the absorbance, also called sometimes optical density. Okay, so okay, let's see a scheme. Yes, that is a scheme of a spectrophotometer. There is in principle also a difference between the light. In reality, what illuminate the cuvette is the blue error are the light involved in interaction with the matter, because there is normally the cuvette is done in a way that is transparent, but it will be never perfectly transparent to the wavelength. So we have to take care, because what we are interested of is in reality is the blue errors, the blue intensity, not the red one. We measure the red one, but we are interested in the blue one. So then we'll see what that need to be done. But first of all, we have to, normally in a spectrophotometer, we have a double beam. No, in the high quality spectrophotometer is a double beam. And so that is the excitation part. So the lamp, monochromator to decide which wavelength. Normally also are a device that can scan automatically different wavelengths that provide at the end the spectra. The same, in principle, the light is divided in two intensity with some mirror, in order that the sample and the blank, and we'll see what the blank is, are illuminated with the same intensity. That's a part of the instrument quality that allow to do this. And so then the light will be detected, and then in the channel of the sample, in the channel of the reference, and it will, the real absorbance that's why it's called also differential in this type of instrument, is the difference between the absorbance of the sample and the absorbance of the reference. So what I said, what is the reference is the everything but the molecule. So because what we are interested in our sample is that the properties of the molecule that are floating in the solution. We are not interested about the absorption of the solvent or the absorption of the cuvette and so. So we are to isolate the absorption and the absorbance of our molecule, we have to make this difference between the sample and the reference. In double beam spectrophotometer is done automatically, so practically this black signal that I represented here is what we get immediately. If you have a mono beam, so spectrophotometer, but you have to measure first the reference. So you like your cuvette containing the solvent, and then you measure the sample, so the cuvette containing the solution, and then you make the difference between the two. Before doing this anyway, so if you are in any case, also for a mono beam photometer, need to be done how to say, the baseline. And the baseline is is how you adjust practically. You settle your instrument, preparing for working. And in particular, what is adjusted in the baseline, which is actually an instrumental action, is not something, is not a measure, is a setting. You measure normally the spectrophotometer with nothing inside, so you just measure the beam, and you practically regulate your zero, because as I said, here you separate the beam, and in principle, ideally, you are expected to have the same intensity in both channels, which is of course ideally, but it's not really the case. It's not really exactly the case. And so then if you measure just the beam passing, and you say to the photometer, if you see two beams arriving with such intensity, even if they are slightly different, but you consider it that that is the zero, that is our things that is equal. So then you educate practically your instrument to provide you the signal that you want. And so, and the same in case with the mono beam, then you have to do this setting before. You do it only with one beam, of course, in this case. So you say the zero, the signal that should be zero, and actually zero in absorbance, but in reality it will be 100% in transmittance. So that is what will be regulated. Okay, so done this, you can then measure so make the measure as we said, and with the absorbance that we get here in black, so then we have the absorbance really of the molecule. And then we can, for example, calculate the concentration using the Lambert-Beer law, which is working in the most of the cases. And how? So, and of course, we have to take care about the path length of the sample. So that is which is normally is 1 centimeter, which is really the dimension that is inside the solution. So it's dimension of the cuvette inside. So it's really the path that is done by the light in the solution. That when we were seeing the calculation was practically the integration of the little element, the L. So then you integrate in all in this dimension. Normally is 1 centimeter, normally, but can be also depending of how thick you make. So there are cuvette with different thickness, and so then of course that reduce the dimension of the solution. Normally the concentration, we work normally with the concentration expressed in the mole per liter, so molar concentration. And so since absorbance has no dimension, is in fact a logarithmic quantity, the extinction coefficient or molar absorption is in molar -1 centimeter -1. And so it's called extinction coefficient because you can imagine that it's related to the ability of the molecule to practically to absorb light. Higher it is, higher is the absorbance. So that means that and lower is the transmittance. So it distinguishes practically the light. But it's also called the molar absorption or molar absorbance, because in fact numerically correspond to the absorbance of a solution of 1 molar. So if you put, considering that 1 centimeter is when the path length, which is the case, is 1 centimeter, so you have to have also 1 here, so you have 1 molar in. And so then the extinction coefficient numerically is the absorbance, only numerically, of course. So then that is so explained. Okay, now let's go to fluorescence. So that is the configuration of a common fluorimeter. And what is typical here, as you see, so is that everything is at an angle of 90 degrees. So we have the excitation part here before the sample and the emission part. So then the lamp, then you have emission monochromator in case you can put polarizer, and then the light hit the sample, and then it will be analyzed by an emission monochromator to have the emission per wavelength and of course detected. With this configuration, of course, we can make emission spectroscopy. In this case, you excite at the fixed wavelength and you tune the emission you tune the emission. So then you scan in the emission to have an emission spectrum. You can make also excitation spectroscopy, and in this case you fix the emission monochromator at 1 wavelength, and you let the excitation monochromator to scan through the wavelength of your choice. And so that is what I was saying when I was explaining the excitation spectra. So then in this case, you see, we have an intensity in function of the wavelength of excitation. So that means that I will see how high is the probability of having emission at a fixed emission wavelength according to the different excitation wavelength that I use. Okay, so this reference cell that is indicated here is that so yes, in the past it was really a cell where there was a solution of very concentrated rhodamine that is practically a quantum counter. That means that is a solution that whose the emission doesn't depend of the so is a solution. So practically we measure the fluorescence. Let's say that we measure like this the fluctuation of the lamp, because of course the lamp as a real object, it's not constant, it has fluctuation, and moreover it depends of the wavelength, the intensity of one lamp. Normally is a xenon lamp. The xenon is an emission that has a spectra. There is a spectra of the xenon lamp, and so that means that there is not the same intensity per wavelength. But that is something that it will be an artifact on our spectra. So then we have to compare practically. So using this reference cell, we have the possibility to measure practically simultaneously the spectra of the lamp, and the signal can be corrected. So then, so in principle, there are also correction in the good spectrofluorimeter for the efficacy. So let's say for the ability of the emission monochromator or the excitation monochromator of transmitting this wavelength, because also this, so the monochromator have an efficiency of transmittance of different wavelength. And so then all these are functions that are generated by the constructor in general. And they are included in the fluorimeter. And when you decide the parameter to visualize, you can apply such correction. The aim is to isolate really the real emission properties of your sample. Let's coming to the story of the 90 degrees. Because in principle there is much more light. So I mean, fluorescence is emitted, of course, in all the direction. So in principle, we could also be at detecting here in principle. So I mean, it's emitted in the same way in all the direction. But here I represent the angular distribution of the scattering light, which, as you see, has a minima at 90 degrees. So, in fact, the light that hit your sample will go through the mechanism excitation emission diagram, Jablonski diagram that we saw before, but is also scattered by the molecule that are in the sample. So they are by the solvent also. So then since they are little particle, and moreover can be also scattered by particles. So let's say dirty stuff that should not be there, but they are there in your solution because it's less not fully pure. But okay, so it can be scattered, and the scattering is much more. The intensity of the scattered light is really much more than the signal of fluorescence. And so then we detect fluorescence at an angle where we minimize the scattered light. Moreover, as you see, the green profile is the case of unpolarized light, and the red profile is the distribution of scattering light orthogonal to the scattering plane. So when the polarization of the light is orthogonal to the scattering plane. So that means that that's why often we, and as you see, is even better. So then it's even close to zero, the scattering in this angle. So it's minimized. So often you reduce, that's true that when you polarize the light in excitation, you reduce its intensity, but you reduce also the scattering light at 90 degrees. And so then basically you have to balance what you have for having the optimal signal. Okay, and so now let's see, that will be a measurement. So we excite. Actually, yes, I was not seeing. So in principle, the excitation is here. So let's say, and the emission, of course, is for wavelength that are higher to the excitation of the wavelength of excitation. And this is the typical structure of a fluorescence spectrum. The peak that you see here are detected because they are photon, and the detector is detecting them, but it's not fluorescence. Actually, this is scattering. In particular, at the excitation wavelength, this very large peak is the Rayleigh scattering. So is an elastic scattering. So is the wavelength of and so frequency is the wavelength of the excitation light that is scattered in all the direction, and also at 90 degrees, even if is minimized for all what we have said, but is there. And so then we detect it. So that's why normally we let to start an emission spectra, not exactly at the wavelength of excitation, but let's say a rule of thumb, 5 nanometer afterwards, in order to get rid of such peak that actually doesn't tell us much. And so this little peak here instead is the Raman spectrum scattering. And that is an inelastic phenomenon, and that is due to the the energy that is lost. So that is involved in the vibration of the solvent molecule. Is very low per molecule, but since the solvent is really present in large amount, much more than the fluorophore, at the end it provides a peak that is detected, and this peak is present at so then it depends. So it's inelastic, so in the sense that it's not the same of the wavelength of the, it's not in the same wavelength as the excitation wavelength, and can be calculated because it depends of the solvent. So, for example, for water, the OH stretching band is quite strong and has this value, and so then we can calculate the where also in wavelength, so in frequency, and then we can transform it in wavelength. So this peak, that it depends of the wavelength. So the position of this peak, it depends of the wavelength that is used for exciting. And you have it one here, and symmetrically also one on the other side. And because it's practically is an energy exchange between the light of excitation and the solvent molecule. And so then it's called, what that is called the Stokes, and that is the anti-Stokes peak. Okay, and finally we have fluorescence. So, but what we are interested in is fluorescence. So normally what we do, and so just to say, so we measured also in red here is the spectra, so of the solvent. And as you see in the spectra of the solvent, we see all what is solvent related. So the Rayleigh scattering and the Raman scattering. Nothing, of course, because in here, because you have no fluorophore. So, and then for isolating the fluorescence, we make the, let's say, we make the subtraction between these two signals, and in green, we obtain just the fluorescence spectrum. We normally also, we have to say that the since in real life and it's not zero this band, because it depends of also some noise of your fluorimeter, and etc., etc. And so with this operation also we clean the signal also due to the noise of the instrument, and we have. So this seems that it didn't change much actually. The green, okay, yes, more here you and but the major feature. So yes, well, let's say when you have a large signal, we can say, yeah, it's a detail. But when you have a weak signal, the story is quite different, because you see the Raman peak can be comparable to your signal. And so then one would say, oh, yes, it's a weak signal, so let's increase the sensitivity of our fluorimeter and give more voltage and so on, and for seeing better. And what happens? You increase the sensitivity of your detector, and so of course you increase all what he can detect, and also the Raman. So it's not, the fluorescence, you see it better, but the Raman is affecting very much. And so there, the correction is even more important, and it's much more evident, the importance. So that is really something that one has to do by default every time you measure a spectra. That's what you have to do. And when you have then your green spectra, your emission spectra, then you can exploit in your experiment. So another problem that you can have in fluorescence measurement is what is called the inner filter effect. So I first explain what it is, and then we'll see how it can affect fluorescence signal. So that is a configuration of your experiment. So it's that the square here is your cuvette. The red dots are the molecule, and the square, the smaller square, is actually the detected molecule, because since we are detecting in square angle, so practically the signal comes from the molecule that are in the center of the cuvette. And so what you do, you excite, and of course the light is absorbed, and so then only a part is transmitted, and you can have you detect your emission. So that is, in general, that's the scheme of what happens. Let's take a much more concentrated solution. So you see the excitation intensity is the same, but the effective intensity that reach the center of the cuvette, where there are the molecules whose signal is detected, is much less. Why? Because all the molecules that are here will also absorb light. It happens also here, but is negligible. But in this case, it's not negligible. So practically, the photons that reach the center are much less than the one that were sent by the lamp, and as a consequence, since less photon, even if you have more molecule that emit, you may have less fluorescence than before. sort of contradicting things, but it's the reason is there because you lost photon. So then it's not the molecule are many, but if there are not enough photon to excite them all, it doesn't matter. So this is a problem that need to be taken care of, because you can you make an experiment, you see, oh, that's we have a quenching effect. So let's see what is the reason. No, it's not a quenching effect. It's simply that the molecule were not excited. So it's a different story. So correction of the signal. There are some formulas that can be used. That is the most complete one that, by the way, for curiosity, was developed in the laboratory where I am working quite some years ago. So I was not there, and yes. So then is a formula. That is empirical, of course. It's not. And it takes care of the absorbance of the fluorophore at the excitation wavelength, the absorbance of a screen molecule. Others can be also at the excitation wavelength, and also a screen molecule at the emission wavelength, because you can have also some emitted light that can be some molecule inside, maybe also your fluorophore that absorb the emission wavelength. Can happen. So then that has to be taken care. And so, yeah, more or less you can adjust this. But it works really when the let's say in a very when the troubles are small, so then you cannot correct really everything. So then when what is better to do is to avoid to reach such high concentration, and so or to use other geometry of the cuvette. So, for example, this is the geometry that is used there, and so then in this case, the excitation light does not penetrate deep enough, and so then the emission light may also be reabsorbed. So practically, I don't see anything. But with this geometry, for example, the cuvette like this, so then is practically, you see, eliminate the diluted sample and filtered. So we can use diluted sample, as I said, to eliminate filtering, to eliminate scattering of the other molecule, or to measure close to the surface, as in this case. So that is, in extreme cases, is that's also can be done. So yeah, let's see also the effect of the inner filter effect, and let's talk about what is said, what is known as linearity of fluorescence. So this is we can measure. Let's say that's in this experiment. That is the measurement of fluorescence of a fluorophore at different concentration. So of course he has a different concentration. Higher is the concentration, higher it will be the absorbance. And I can and I plot. So that is the plot, the fluorescence signal in function of the absorbance. So first, the absorbance is measured, which is linear with the concentration to a very large extent. So there is also saturation also in this case, but very, very, very extreme large concentration. So in this range is linear. And I plot fluorescence in function of the absorbance. So And what we observe is that in initial, so of course, I increase the concentration, I increase also the concentration of the fluorophore, so I increase the signal, and the fluorescence is increasing, and increasing linear. Then start to increase, yes, but less, till even decreasing. And that is the consequence of the inner filter effect, which I don't see in absorbance, because absorbance is measured in the through the cuvette. So at the and so then taking care exactly all the absorbent, all what is absorbed everywhere, but I see it in the fluorescence, this saturation. So practically, fluorescence is linear in absorbance, typically till a value of 0.1 in absorbance. Afterwards, not anymore. So of course that it depends. So that means that if you have so is given an absorbance value and not a concentration level, because it depends of the ability of your fluorophore to absorb. So that means that it depends of its extinction coefficient. And so that means that if you have a fluorophore that absorbs very much, that has very high extinction coefficient, then you will, even at low concentration, you enter in the troubles of the inner filter effect, because you lose photon in the first millimeter of your cuvette. So that's why it's taken the absorbance as so practically that means that when the light that is lost here is below 0.1, and so that means 10% of the transmission, you can neglect this problem. Afterwards, not anymore. Okay, so, but the fluorescence, we said, is more sensitive than absorbance. And so if we use absorbance to detect the concentration, but if you want to have if you want to detect a lower concentration, maybe we can use fluorescence. And he said, yes, in fact, is a yes, but so then you can use fluorescence also to calculate the concentration, but you have to work in samples that are so diluted that their absorbance is less than 0.1, because it's in this range that fluorescence is linear with the absorbance and so the concentration. Concerning the geometry of the cuvette, here I put some section of typical cuvette that are using in our experiment. And so that is a cuvette that has a section 1 centimeter per 1 centimeter. That is also very common, which is so basically this wall of the cuvette are thicker, and so in the solution is occupy only 1 centimeter per 4 millimeter. Then there are also 2 millimeter, even 1 millimeter. So that is so there are several reasons, but that is very common, which let's say is a good compromise between not using so much solution because we reduce the volume of the solution. Sometimes our samples are very costly, very expensive, and still having a good signal, because of course if you reduce the molecule that you observe, you also don't have so you reduce also the signal. Okay, in case you have troubles with the inner filter effect, you can, for example, turn your cuvette like this, and so then you will reduce a little bit the signal, because but actually, so no, you don't really reduce the signal. In fluorescence, you reduce it in absorbance, because there are less cuvette, less fluorophore that are absorbed. Okay, so that is also another way to. So that's our like little tricks can be used for getting rid of this problem of inner filter effect and maybe remaining in the linearity region of fluorescence. So now let's see also what this some analysis of a mixture of fluorophore, and so some real experiment that they were done. So then is a mixture of tryptophan and tyrosine, which are two fluorescence natural amino acid in protein, and you see they absorb in that is a normalized, so that is the spectra are normalized just to show the difference in shape. So the black is the tyrosine and the red is the tryptophan, and alone, and the blue is the mixture. So okay, so then it's a little bit difficult when you have a mixture to separate what is where the tryptophan absorb. Okay, but we have to say that tryptophan and tyrosine. So there is also a very famous wavelength that is used when you are when you want to select the tryptophan in a protein where you have also tyrosine, and this 295, which is a wavelength that is approximately here, where the tryptophan absorb still reasonably, but the tyrosine practically almost not anymore. So, okay. And so what we do, now we make the fluorescence. So we excite at the wavelength where both excite, for example, 280, that is somehow the maximum for tryptophan, and close to the maximum, so tyrosine 276 or something like this, more or less. And so then, and here we have excite 280, so we have a spectra of the tryptophan in black alone, of the tyrosine in red. As you see, they are quite different. So the tyrosine emit at around 305, something like this, and but they overlap. And when you have a mixture, you have the green spectra. And we analyze our mixture. So how to see at which wavelength, because at which wavelength we have more contribution of tryptophan than tyrosine. But we make an excitation spectrum, and so that is the next one. So so here is an excitation spectrum. So is practically fluorescence that occurs before the wavelength of emission, as you see here, and so this peak, that is the Rayleigh scattering. Because let's take one example. Let's take the black one. The black one, what it is, so is an excitation spectra. So is the fluorescence that I detect at 350, and I scan from I don't know, most likely 250 till 360 to include this. Okay, so then practically that tells us that if I observe the fluorescence at 350, so all this is fluorescence detected at 350. All the black spectra is detected at 350, but is plotted in function of the lambda of excitation. So I change the lambda of excitation one by one. 260, 61, 262, etc., 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 etc. And I still detect the fluorescence 350. Of course, when I arrive at 350, is the same wavelength emission of excitation, so now I have my Rayleigh spectra. If you observe the shape of the curve is quite close, actually, is respecting perfectly the shape of the absorbance spectra of the tryptophan. In fact, at 350, tyrosine doesn't absorb and practically doesn't emit. Tryptophan instead, yes. So that means that the fluorophore that is responsible to the emission at 350 is the tryptophan, and in my excitation spectra, I see it. If I go to 300, so is the green spectra. Yes, unfortunately, the color code it's a little bit unfortunate. If I take 300, so that says actually is 305. That's I would say. I took some old experiment and yeah, I have to change. Oops, sorry. That should not. I want to. Good. 300. Yes, let's say 300. Yeah. Tryptophan doesn't emit, but tyrosine, yes. And in fact, for what we see is that responsible of the emission at 300 is tyrosine. The spectra that I obtain is practically exactly the profile of the spectra of the tyrosine, of absorbance of the tyrosine. So is not in this range, 250, 300, is not the only amino acid that I that absorb. It's not only the amino acid that absorb. Also tryptophan absorb, but it doesn't contribute to the emission at 300. So that's why fluorescent-wise, I see only tyrosine. If I am in between, of course, I see something in between. So in this case, both fluorophore are contributed to the fluorescence at 320. Okay, so this is how it's with the excitation spectra is how we can actually separate the contribution. So that's, of course, if we measure a mixture, so like we may make the green spectra, so then we see that we have two bands, and then we without knowing the real emission spectra of the two species, let's say that is an unknown solution. And so then what we will try to make excitation spectrum choosing all the different several wavelength and see these excitation spectra, how they evolved, and so, and then maybe we can isolate the profile of two or even more compound. In the next, here is actually the effect of the inner filter effect somehow. So here is used the 320 as a wavelength of emission, and is an excitation spectra, and so is. So they are normalized. So in principle, the intensity would not be the same here. They are normalized just for comparing the shape, as also was done here actually. And so the black one is measured at low concentration. Okay. Then we measured an excitation spectra at high concentration, but with this orientation of the cuvette, which minimize the inner filter effect, and we have practically the same shape of the spectra, more or less actually. It's the same shape of the spectra, of course, because it's the same things that I measure. I just change the concentration. So that is, and then I measured with the same high concentration, but with the cuvette in this way, where instead the inner filter effect is not minimized. And as you see, the spectra change in shape. And actually here is also flat in principle. This is in real value is deformed because the signal is disturbed by the fact of the inner filter effect. So that is just also to see it, to show it. Okay, so then other problem and solution. So fluorescence is good because it's sensitive to physical chemistry property of the solution, temperature, pH, and oxygen, for example, and more. But because of this, we have to take care, because it's good and not good. Because yes, if fluorescence is depending on the temperature, then we have to know what we want to measure. So the temperature normally needs to be controlled, because we want to in our sample, we want to know the characteristic of our sample, and we don't want to detect the signal change due to temperature. So then the thermostat in our fluorimeter is an essential element. Then we can, of course, also change the temperature. We can also make measurement in function of temperature, because we want to do this, for example, in some melting experiment. But okay, we have to control it. So then the pH is also need to be controlled, because since fluorescence can depend also on pH. So, or we want to measure, we want to follow the pH change. So like somehow using a fluorophore as a pH indicator, okay? But anyway, we have to know at which pH we are measuring. So the pH need to be controlled. And in specific circumstance, when we have, for example, samples that are redox sensitive, so we need also to degas the solvent, to avoid the presence of oxygen. So then problems that you can have with the fluorescence, when we are playing with lights, so we can photodecompose our fluorophore if we excite with too intense light, and that is a chemical effect, or photo bleaching, that is a physical effect. So that means that you basically kill it, you kill the molecule, and then you don't see any signal anymore, or a decreased signal. So what to do for avoiding this problem? So to avoid long excitation time, to optimize the intensity of the excitation source, you have to make some control experiment, and you know that more than that intensity is better not to go. And also steering the sample in order to renew. So if you kill molecule, then you renew the molecule in the central volume. So that's can help till a certain extent. but that's we were actually already observing. So the optical saturation, so the inner filter effect when emission intensity is no more proportional to the excitation intensity, and so that's a problem that we have to take care, as we say, balancing, so finding the right concentration, geometry of the cuvette, and etc., etc. Then another phenomenon that can happen is the adsorption, which consists in a non-specific binding to the surface, and that happens that there are some molecules that like to be adsorbed to the wall of the cuvette. When I was younger, I was working with a protein which unfortunately was doing this. And so that was practically the consequence of this effect, was reducing the fluorescence signal, because since the protein was mainly attached or close to the wall of the cuvette, was not anymore in the center where I was detecting it. And so then the signal was lower than expected. So this is also a problem that affected the signal, and we don't want. So for solving this using low binding materials for TIPS and Epperdorf, in this case, steering is negative, because when you steer, you practically invite the molecule to go on the wall. And then in case also there are specific agents that reduce this adsorption, like silicone coating of the wall of the cuvette. Of course, we have to be careful, because every element you add in your system, which is not the system that you want to observe, you have to be aware of the possible difference, and so there control experiment with and without to see what that, so that need always to be done. And then also in case you parameterize the shaking procedure, that what does it mean? So then I don't know if you see me, but I try to explain it also with words. So that means that imagine that you are measuring a binding, and so then that means that you add your receptor, you measure, then you add your ligand, and before measuring again, you shake the cuvette, so you go up and down, so you in order to shake the solution, and so on, and then add another, and then you measure, then another concentration, you shake your cuvette, and so on. And so this is every shaking, if you have something that adsorbs, is also an invitation to go to the wall. And so that's something that I was also doing it with this protein, and I was working on measure binding concentration to its ligand. So I was practically doing making a shaking really only in so let's say one shake up and down, then I was turning of 180 degrees, so in the section, and I was practically shaking again up and down, practically in another direction. So that's it. And I was measured this several times with the protein alone. Okay. Sorry.
Yes, Alicia.
The question?
No, not questions. I think it's you can, if you want, you can continue next tutorials also these things, or you are going to finish.
Yeah, I think it's not much. It's not much more. I think if it's fine. Okay. If it's fine, I think there are 2 or 3 slides, and so yeah, that's his. Yeah. And so yes, okay. So then I was seeing practically how the signal was changing in function of a specific shaking, and then this I was using this for correcting the signal when I was really doing my titration afterwards. Okay, so yes, actually that's is important things that I would like absolutely to say is fluorescence quantum yield. We were talking about but never seeing how is measured. And so, yes, actually, quantum yield is practically definition is the ratio between the emitting photon and the absorbent photon. So is the yield of emission. So yes, how much of the photon that were absorbed I will detect also by emission. And so then normally, so I mean, if you want to do things really extremely correctly, and that's normally is done in the standard bureau, in the bureau standard, you use an integrating sphere, which is practically you detect the fluorescence in all direction, and so you really you don't lose anything. So you really have a measure of the real fluorescence. That's normally every day you don't do this. You don't necessarily have this instrument. And so what is done practically is the following. So yes, that is what we have to measure. So now, what is a parameter that is proportional to the emitted photon? It's the emission spectra. And what is the parameter that is proportion to the absorbed photon? Is the intensity of absorbance, that is the absorbance intensity at the wavelength of excitation. And so, okay, so for so you see the and so that is actually the formula that is need to be used for calculating the quantum yield. So here there are a few things to be said. So let's focus on this ratio here with X. So that's X is our sample that we don't know. And so the surface of the spectra of emission is this parameter that we want to know, is practically the number of the emitted photon, because a spectra, as I was trying to indicate here, is a sort of histogram. So is a probability of emitting? Yes, okay. And also it gives us, so that means that there are more photon emitted at this wavelength with respect to that one. So then imagine to have an histogram, in principle should be continuous everywhere. So that means that if you get the surface, you integrate the spectra, you get a parameter that is proportional to the photon emitted. And then you use the intensity of absorbance here in red, and is the parameter that is at the wavelength of excitation, and is the parameter related to the proportionally to the absorbed photon by your sample. The point is that one will say, okay, it's enough, I have it. No, I don't, because fluorescence is a relative parameter. The unit of fluorescence, as you will see in every paper, is arbitrary unit. You see also AU all the time. And because there is no unit of fluorescence, the unit depends on the type of fluorimeter that you have. So you have a fluorimeter that they have a photon counting, so then you have a number of photon. In other fluorimeter, when you have a photomultiplicator, you have a voltage or a current. So that means that if you measured with a sample, the same sample with different fluorimeter, you may have different signal, different intensity, because this signal and is not for such a reason. So to make an absolute parameter is required to measure in the same condition a standard for which we know the quantum yield, And so then we do the same. We make excitation, so absorbance and the surface. So then sometimes there are standards that need to be in a solution that may have a different refractive index. And so that's in principle to be really careful. Also the ratio of the refractive index is required. Normally we work always with the aqueous solution so that this parameter is practically not affected. And so then we get finally the quantum yield by comparison to our standard. And this is a parameter that is between 0 and 1, or 0% to 100% of emission. And it tells me how powerful is the fluorescence of my compound. And normally, so there are few compounds that then we see that are a quantum yield close to 1. Normally, is always much lower. And this parameter is absolute. So you measure it with a specific fluorimeter, but this way of calculating practically cancel the specificity of your instrument, and the parameter that you get is something that you can publish, you can communicate it to your community, because it will be obtained the same also with another instrument. Good. So, okay, for measuring, you have to be cuvettes. Yeah, normally the standard cuvettes are used. 110 millimeter, and the concentration range actually has to be, again, to minimize all possible problems, and in particular the story of the inner filter effect, both in the standard and in the emission. And so then it's better to have always this absorbance in both cases lower than 0.1. And another advice for also be sure that you compare comparable things possibly, it's better to choose a standard that has a spectroscopical property in the same wavelength range. And so then where your fluorimeter, of course, work in the same way, detect in the same way for the sample and the standard. And just because standard we are saying, so these things are in tables, and you can choose. So you see that is, for example, is taken actually for the book of Bernard Valeur. So here there are some compound that can be used. As you see, the temperature for which the quantum yield is what it is. That's the solvent in which they are used, and the range for which this standard is working well. That I just underlined that for protein, normally that is the range of the emission of the intrinsic fluorescence of protein, and tryptophan is what is used for tryptophan alone in water is what is used for having it. Okay, so I think that I can maybe stop here, and I don't know what is. Yeah, okay, was less. I think that the major things were said. I can stop here.
Yes.
Okay. Yeah. Don't know. Do you have
So
questions?
If you have, any questions? I think many of the students actually left because time is 4:30. So more than half an hour.
Okay.
You talked more than half an hour.
Oh, okay. So yeah, but I mean, I was starting at 20, so I have just 10 minutes. Sorry?
Yeah. You
No,
have taken more extra. That's why few
okay, no,
students
because
they were left. Yeah,
okay, I thought
but
it
it's
was an
okay.
hour. It was an hour the tutorial, no? Or was it half an hour?
Yeah, it's a 1 hour. Yeah, yeah.
It's 1 hour. Yes. Okay. So yes. Okay. In my is yeah. I was talking 10 minutes more because I was starting at
Yeah.
20 and 10 minutes
Mhm.
more. Yes. Sorry. Yeah. But
But
yes,
it's
as I said,
yeah.
I mean, so many things.
It's
But okay.
okay. So if you have the students any more questions, then you can ask Alicia in the next talks and the tutorials.
Of
So
course.
Alicia have a next talks and then tutorials. Next day Alicia have a talk and tutorials Alicia have on Friday. So if you have any questions, you can ask during that time also.
Dr.
Yes. Okay.
Jagannath,
Yes. Yes.
hello, Dr. Elisa. This is Dr. Avasthi, Dr. Pamita Avasthi. Uh,
Uh,
I would request Dr. Jagannath to share a schedule with you, and it's okay because the lecture was really good. It has extended to another half an hour. We had not informed the student earlier, so, any queries or any questions they can have with you one on one and during the next session, or they can post you, right, via email, or we
yes.
will
Of
post
course.
you via email. That
Of
depends.
course. Of course.
That
Of
can, I
course.
think that can be
And
done
so
that way.
yeah, of course. And actually, there was also a little problem that was increasing the delay. Is that because in the schedule I was observing there was practically no break planned between the lecture and the tutorial. So was and so then
No,
yes.
it's
So
okay from our
You
side.
can
It's
that
okay from
was
our side. Yeah, we will just
okay.
inform the students because sometimes the lectures ends a little bit early. Sometimes it got delayed. So this was the first day we had a inauguration session also. So things got a little bit delayed. So there is no issue. Lecture start
Okay.
means for the first day it is something. Next day it will come its own time. It's okay. It was really
oh,
good, and
Okay.
your lecture is obviously online, so they can see it again. Not an issue.
okay. It's
Okay.
perfect, Alicia. Everything.
Thank you so much.
Yes, we can take break after
So
lecture, after 15 to 20 minutes, whatever you required, not a problem. Okay, so
okay. So
it's
this is
perfect. It's all everything is perfect. Great. Yeah.
okay, so then I hope that was responding to somehow your expectation of because of course it's that belongs to the program of the school. So please tell me.
Of
I need
course,
this
of course,
feedback. Okay,
of course,
so
indeed, of course. Uh-huh.
okay, so
Okay.
great,
Perfect.
and so then
Everything's
yes,
perfect. Great.
tomorrow I will be maybe more on time, and I will also how to say maybe there will be also less technical problem, and so let's hope that will be more more in time.
Yeah. Yeah.
Okay,
Yeah. Yeah. So if
so
yeah, perfect. Good.
so
Okay.
then see you
So thank
see
you
you
so much.
tomorrow.
Yeah. See you
Yeah,
tomorrow. Thank you
and
so
Thank
much.
you.
It's a
Thank
great
you.
talk. Nice talk. Thank you.
Thank you.
okay.
Thank you. Thank you.
Okay,
Bye
great. Okay, so thank you again. Have a nice evening,
bye.
I guess, for you, and see you
Yes.
tomorrow at 10:30 as again for one lecture.
Yes.
Okay,
Thank
Perfect.
you.
good.
Perfect.
Thank you.
Thank you. Thank you.
Yes.
Thank
Bye.
you. Bye bye.
Bye. Bye.
Simran, please announce for tomorrow. So I request the participants, they can leave, they can join the session tomorrow around 10:30. Thank you very much.
Okay, ma'am. Thank you.